did you get a chance to look over the Mendelian genetics packet I just posted an answer key this morning? So I want you to maybe take a minute and look yours over. If you turned it in, you got the answer key. I'll double check and see if I need to catch up. Anybody I need? Nope. So I wanted to field questions on that Mendelian genetics. Anybody who maybe you started working on it and you got stumped on something, or those of you who got it returned with an answer key, look through it, see if there's something you disagree with and you want to ask questions about that. So you can share in the Google or in the chat box if you have any that you were stumped on or wanted me to talk you through. Alex, I think, so where it misaligns, it looks like there is an extra question added in. So there's a question about the genetic recombinations, these questions here. So first of all, crossover frequency, you understand background in that, like, you have two different chromosomes, right, that are carrying basically the same information, and we have some genes found on our chromosomes. So you're going to remember prophase 1 of meiosis and how you can have like tangling up of the chromosomes, right? And there's some crossover event. So like these maybe broke off. Okay, that doesn't work. And they switch spots. So so anyways, if this is A and B, right? A and B, maybe this is a dominant B and this is a recessive B, and then they swapped during prophase 1, crossing over. So what we find, and this is Thomas Hunt Morgan who came up with this, and so he came up with his own unit of measurement called the centimorgan, and it's a relative term basically. So each centimorgan distance is equal to 1% crossover. So in this case, A and B are 24, they cross over 24% of the time, which means they're 24 units apart. Okay, so, whoa, I just want, let's get rid of this for a second. I'm gonna just draw a line if I can. And then if A and B, so when I'm doing a crossover, when I'm doing a gene map, I like to start with the ones that seem to be furthest apart. And so they serve as bookends. So A and B are 24% apart, or 24 centimorgans apart. Okay, so this is just some random relative 24 distance. Okay, so if A and C is 11% different, so they're 11 units apart, I have to decide, is C to the left of A or is C to the right of A? So then I want to see, where is C in comparison to B? If C was more than 24 from B, I would know that C is to the left of A. Since C is smaller than 24 away from B, I know that C lies somewhere between A and B. So it's 11%, maybe this is halfway. So it's 11 units from A and 13 units from C. So I'm going to put C here, and this is 11, and this is 13. Does that make sense? If crossover occurs more than 50% of the time, you can assume that these two genes are on separate chromosomes. And so they're sorting independently rather than having a crossover event. Any questions on that one? Or any others from this packet?
Yeah, could you repeat what you just said about like the 50%?
50%? Mm-hmm. Yep. If crossover occurs, 50% of this, or like if two if there's a crossover frequency of 50% or greater, you can assume the two genes are on separate chromosomes, and therefore they're sorting independently of each other and not found on the same chromosome. You would, chromosomes or genes that are found on the same chromosome, you would say they are linked. Linked traits travel together. And I am, for the sake of that, looking up my gene mapping part. And I'm going to switch over to this. So this is what I was just saying. Genes with recombination frequencies less than 50%, you would assume to be on the same chromosome, and therefore it's a crossover event rather than an independent assortment. You refer to all of the genes on one chromosome as a linked set, linked groups. If two genes are not inherited together greater than 50% of the time, you would assume they are on separate chromosomes and are unlinked. Which two genes do you think would most likely be separated during a crossover event? Any two genes on here that you think would likely separate during crossover? You can throw it in the chat box. You can shout it out loud. Dumpy wings and brown eyes. Okay, so dumpy wings and brown eyes are quite far apart. Like 100 units, 120 units apart. 100 units apart, sorry. So they would likely separate. What are two that would likely not separate? Arc wings and black body would likely separate. But two that are close together, any of these here, not likely to separate, right? Black body, reduced bristles, purple eyes, they all occur very close together. So it's not likely that they would be separated. So a crossover, if you think about it, like how many chances are there that you could tangle up a chromosome between here and here? I mean, I could just randomly go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just made 10 different cuts, and therefore there's 10 different ways that could recombine, right? But if I were sorting between any of these, like black body and purple eyes, 1, 2, oh, there's only like 2 cuts I could make. So it's just not as likely because they're close together, okay? I can throw this PowerPoint in, it just kind of summarizes that whole bit, okay? So I will, I'll put this in the Google with today so that you can look at that in a little bit more detail if you want. Any other questions on the packet before I blow your mind with chi-square analysis? Anytime we do like problem solving, things get a little bit longer. So today is a little bit longer because we took time to actually look over our work, right? So some of you have not yet turned this in. If you're still struggling with pieces of it, you can stay on after we get done with chi-square and I can help you with that, okay? I bought that darn pen so that I can write on my screen and I still haven't figured out how to use it. $50. Okay, so in the Google world, today we're doing chi-square analysis. There's a video. You can watch that one today. There's a couple more Mendelian genetics. Watch them sometime this week, okay? I'm going to give you a chi-square quiz on Friday, so be ready to apply what you learned. All right, so statistics are used quite often in science because we never get exactly what we expect, right? So we have to decide if the difference that we're seeing is significant. So we can't just say, oh, it's 12 apart, so there's a significant difference, unless we've actually done some sort of statistical analysis of it. So there's a t-test, there's standard deviation, there's chi-square, and today we're going to do the chi-square. Okay, so it's a statistical test commonly used basically to test if the results fit your hypothesis. Okay, how well do your experimental data fit expectations? So this is often called the goodness fit, goodness of fit. Chi-square, this X is coming up, okay? It's 2 slides away, sorry. This is the chi-square. This is sum, observed minus expected squared over expected. I'll slow that down and tell it to you one by one. Okay, so you're going to start with a null hypothesis. A null hypothesis is basically saying there is no difference between your results and your hypothesis. Okay, so what you're expecting. So if flower colors is completely dominant, then the offspring of a heterozygous cross, meaning big P little p, crossed with big P little p, will appear in a ratio of 3 to 1, purple to white. So in order to decide what you would expect, you want to run a Punnett square, right? So if you had 2 heterozygous individuals and you cross them, you would always get a 3 to 1 ratio. You know that. So out of 400 crosses, 300 should be purple and 100 should be white. So your null hypothesis would be that there is no difference. You're going to get 300 purple and 100 white. So in order to do this, you have to be able to determine the expected value based on a Punnett square cross or using rules of probability. Okay, so remember Mendel used F1, F2. The parental cross was the purebreds. The F1 cross was the hybrid. And then the F2 cross, the next generation, is where we saw that hidden trait reappear. So you count your F2 cross and you get 290 purple instead of 300. You get 110 white instead of 100, right? So we're expecting a 3 to 1 ratio. We're expecting 300 to 100. Is this difference significant enough to reject your hypothesis? Or can we expect that much variation simply due to chance? That's what we're trying to figure out. So here is your equation, and you'll have a formula sheet, right, with AP. So in the formula sheet, this formula is there. You just have to be able to use it, okay? So X is the Greek letter chi, not chai. You drink chai tea. Chi-square, okay? And we're not solving for X. We're solving for chi-squared. So you're going to leave it in that squared version. This backwards E is the Greek letter sigma, and it means to add up everything that follows. Okay, so you're going to have an observed minus expected squared over expected for the purple, and you're going to have an observed minus expected squared over expected for the white. So this means to add them together. Okay, observed is what you actually saw. You counted 290 purple, you counted 110 white. Expected is what you would mathematically expect. That's your Punnett square or your laws of probability. So we expected 300 purple, we expected 100 white. Always use numbers of individuals, not fractions, not percentages. Like you expected 3/4 to be purple, or you expected 75% to be purple. You don't want to use those sorts of numbers. 0.75 in a frequency. You only want to use actual numbers of individuals, a data count, okay? So if Now we just plug in our numbers. So we expected 300 purple. We observed 290. We expected 100 white. We observed 110. So we're going to set this up. So 290 minus 300 squared divided by 300 is 1 set. We're going to add that. That's my sigma sum to the white. So this is the purples and this is the white. 110 minus 100 squared divided by 100. And really the purpose of squaring it is to get rid of any negative numbers. So when I square this, when I get this one, I have negative 10 squared divided by 300. That's my purple. And I will add that to my 10 squared divided by 100 for my whites. So when I do that, I square them and I get 100 divided by 300 for the purple and 100 divided by 100 for the whites. So just simply add those together. 0.333 plus 1 is 1.333. Okay, solving for chi-square. So you're not looking for the square root and solving for x. So you leave it in this version, chi-square. 1.33. So what do I do with that number? I have to apply it to this table. So you have to understand this critical values table. So this is goodness of fit. So where do we find 1.33 on this table? Where does it fit? We need to know a little bit more about the table. So first of all, P, this top row, is your probability. DF refers to degrees of freedom. The degrees of freedom is the number of variations you have minus 1. The number of variations you have minus 1. So we had a purple and a white. Our degree of freedom is 2 minus 1, a degree of freedom of 1. If I had 4 different variations, I'm counting M&Ms, and they could be red, green, yellow, blue, brown. There's 5. The degree of freedom, variations minus 1. For that example, you would have 4 for your degree of freedom. So in this case, my degree of freedom is 1. I only need to look at this top row. Where does 1.33 fit on this top row? 1.33 is greater than 0.455. It is less than 2.706, right? So our number is falling between a probability of 0.5 and 0.1. That means I can expect variations to this extent 50% of the time. I can expect variations to this extent 10% of the time. So variations between 50 and 10. In science, we allow a 5% variation. So we can assume results will vary due to chance itself 5% of the time. If we look at this row alone, 0.05. So in our class, we will only look at 0.05 probabilities. Okay? So that's the cutoff to reject a hypothesis. And basically it's saying you can expect variations due to chance 5% of the time, like to this extent, that much variation 5% of the time. If your number is greater than 0.05, this is saying you're only going to expect variations to be 2.5% of the time, 1% of the time, 0.005% of the time. So they're saying whatever variations you have are not due to chance. Over here, this is saying you have either experimental error or you need to go back and revise your hypothesis, because we would not expect those variations, that amount of variation. If the number is lower than over here, then we accept our hypothesis, or we fail to reject. You never accept. You reject or you fail to reject. So this would be acceptable variation. It is not a statistical difference. Okay, so numbers on the low side over here, good. Numbers on the high, bad. And for us, we landed somewhere between 50% and 5%. So we accepted that. Our number was over here, 1.33. Okay. So our critical value, you refer to this number here as your critical value. The critical value at 1 degree of freedom and 0.05% probability, our critical value to beat is 3.841. Anything greater than that, we will reject our hypothesis. Anything lower than that, we will fail to reject our hypothesis. That's what I just said. So we just kind of walked through that. This is a dihybrid cross. This is a dihybrid cross. So here's what we observed. Remember, if you're doing a heterozygous cross with dihybrids, you have that 9:3 to 3:1 ratio, right? So we observed this many round yellow, this many round green, this many wrinkled yellow, and this many wrinkled green. And we're hypothesizing that these are linked genes, and they're just sorting independently, right? So if we did the cross, we would have a 9:3 to 3:1 ratio, and we have these expected results. Okay. So with that, would you be able to do a ChiSquare analysis on a piece of paper and pen? In this case, you have 4 versions that you'll have to add up together. So you're going to do observed minus expected squared over expected, plus observed minus expected squared over expected, plus observed minus expected squared over expected, plus observed minus expected squared over expected. Can you do those 4? So you want to look at the total number that you counted. So in this case, we didn't have an even number. We counted 556 total flowers, or whatever, keys. We were expecting 9/16 to come out round in yellow. So I'm going to multiply that times my total to get how many I expected. Round in green, 3/16 times the total to get my expected value. Expected for wrinkled yellow, 3/16 times the total to get my expected value. And wrinkled green, which is double recessive, right? 1/16 times the total to get my expected value. Tell me to wait if you want me to wait at this point. So now we plug it into the formula. And we have to do this for each one, right? Because we're going to sum each of those 4 variations. So this is our green yellow, no, brown yellow, brown green, wrinkled yellow, wrinkled green. If I did that off the top of my head correctly. Okay, so this is our observed minus expected squared divided by the expected. Da-da-da-da. Add those all together. That's the sigma sum. Here we go. And we get a 0.470, which seems like a low chi-square. But to determine if it is, we have to look at the chart, right? So degree of freedom, we had 4 variations. 4 minus 1 is 3. So that tells me where I'm going to look on the chart. We are going to always use the 0.05 p-value to determine our critical value. Okay, so I have a degree of freedom of 3, and here's my 0.05, 7.815. That was the number to beat. 0.4, whatever that was, very low number, right? So it's over here somewhere. So 0.470 is less than, so we fail to reject the null hypothesis. We never say we accept it because, I mean, there's still a chance, right? But we're only going to be wrong. Like if you were at 0.05 probability, your results will be wrong only 0.05% of the time. And we were way at like, so degree of freedom is variations minus 1. The number we care about, 0.05. Anything lower than that, as far as critical values, chi-square lower than, you accept or fail to reject, sorry. Anything above that, you would reject the hypothesis, which means go back and try it again. And that's as far as I want to go. Okay. So now you're going to slow that down a little bit with the POGO. There's a short video I want you to watch. You know, try to digest that a little bit, maybe do a little bit of POGO. Watch the video, get that done today. The POGO is not due till Wednesday. Okay, so in AP Central, I'm going to be looking, this is what I do on my end. We are in Unit 5. And this is daily video 3. So look at 7% have already watched it. Good job. So that's how I check to see if you have it done. Now, Alex and Grace are going to mark done. They're all set. Okay, so after you guys watch it, remember you have to play it out to the very end in order for it to move you from this row to this row. And then mark done in the Google World. Okay, so that's chi-square. I also posted some exam review material. So PowerPoints, these were done by students as an assignment. They're all very good PowerPoints. You'll find Ian's brother, I think, has one of these in here. And then the topics, sorted by topics, and then I tried to make questions. You don't have to give this to me, but this should drive your studies. Things that are in blue are the things that were on last year's final exam. So you can pay special attention to that. What questions do you have for me? We had a lot today.